Welcome back to this channel. In this video, we shall take a closer look at rotational kinematics. Rotational kinematics refer to rotational motion with constant angular acceleration. What that means is the angular velocity of the system is increasing or decreasing at a constant rate. For example, let's look at a disk that is spinning counterclockwise like that. This is the reference line, and the spin axis is exactly in the middle and coming out of the plane. Now let's assume the angular acceleration for this rotational motion is constant. We know that angular acceleration is related to angular velocity in a following manner. So in a given example, since the rotation is counterclockwise, the direction of the angular velocity, as we have discussed in previous video, is coming out of the board. Now we can rewrite this derivative equation in terms of integral in a following manner. The integral of d omega, omega being the angular velocity, of that rotating cylinder or disk equals alpha dt integral. However, we know that alpha is a constant because we are talking about rotational kinematics, so this alpha can be taken out of that integral sign, giving you alpha times the integral with respect to time. Let's assume the system here, when at t equals to 0, the angular velocity is omega I, referring to initial angular velocity, and at time t, the omega is angular velocity at any time t. So that means this expression can be written as omega at any time t minus omega initial, namely omega at t equals to 0, equals alpha t. So the angular velocity of this rotating disk at any time t is given by the angular velocity at t equals to 0 plus the angular acceleration that is constant times the time t. So this is the first equation of rotational kinematics. It has the same form as the kinematics equation for linear motion, in which this linear speed at any time t equals the initial speed at t equals to, say, 0 plus the constant acceleration times t. Remember this? This is the rotational analog of this equation. Now let's look at the second equation of kinematics. This involves the angular coordinate. Now we know the angular coordinate is related to the angular speed in a following manner. The rate of change of that angular coordinate with respect to time equals that angular speed, or angular velocity. Angular coordinate is measured with respect to some reference line. In this case, let's take that horizontal dotted line to be the reference line. So if you concentrate on one point at the circumference of that rotating disk, its angular coordinate is measured like that, theta. So let's see how the position of this point varies with respect to time. So using the same trick, we invert this equation into an integral form, so you get omega dt. Now keep in mind, omega is also a function of time according to that first equation that we derived. Let's assume at t equals to 0, the angular coordinate is theta initial, like that. At any arbitrary time, the angular coordinate is just theta. So theta I could be arbitrarily that angle. So what that means is we start measuring this rotation when that point here was there. Let's substitute this expression for omega as a function of time into that integral, and we get the following. Omega I, which is a constant, plus alpha t dt. So the left-hand side of this integral, of this equation, is theta minus theta I. The right hand side, omega I, is a constant, can be taken out of that time integral, and that will give you omega I t plus alpha over 2 t squared. So there we have it, the second equation of rotational kinematics. The theta minus theta I is the angular displacement measured in the units of radians, equals omega I t plus half alpha t squared. This is the second equation of rotation kinematics. The third equation comes by eliminating time using these two equations. If you take the time from the first equation, that's going to give you omega t minus omega I over alpha, and you substitute this t in here and also in there and do the algebra, you will end up with the following expression. We will skip the algebra and simply give you the result. It's going to be omega squared minus omega I squared equals 2 alpha delta theta. So this is the third equation for rotational kinematics. Let's see how to use these equations in problems. So the first problem, a rotating cylinder's angular velocity decreases from 3.5 radian per second to 2.5 radian per second in 20 rev or 20 revolutions at constant angular acceleration. Find that constant angular acceleration of the cylinder. Let's see what are the numbers that are presented to us. We are given the initial angular velocity, that is 3.5 radian per second. We are given the final angular velocity, which is 2.5 radian per second. We are told that the angular displacement the cylinder has gone through in the unit of revolution is 20 revs. Now, we have to turn this revolution unit into radians. 1 rev is 2 pi radian, because in 1 rev the cylinder will rotate through 360 degrees. So 360 degrees is 2 pi radian. So if it's 20 revs in radian, it is 2 pi times 20 radians. That is the angular displacement that the cylinder has rotated through. There is no time mentioned up to this point, and we want to determine the angular acceleration alpha. So the third equation would enable us to determine that. Remember the third equation? Omega squared minus omega I squared equals 2 times the angular displacement times alpha. So when the angular displacement is that, omega is that. So it's 2.5 squared minus the initial angular velocity is 3.5 radian per second, so square that, equals 2 times delta theta, which is the angular displacement, and we know it is 40 pi in the unit of radians, times alpha, and you can solve for your alpha. The answer that you're going to get is minus 0.024 radian per second squared. Now notice you are getting a negative answer. And the reason for this is because the angular velocity is decreasing from 3.5 to 2.5 radian per second. It's slowing down. So it makes sense that you're getting a negative answer for angular acceleration. So this is the answer for part A. Now let's do part B. How much time did the speed decrease take? To do part B, we can use the first rotational kinematics equation that says omega at time t minus the initial omega equals angular acceleration times time. Now we know the final angular velocity is 2.5, so 2.5 radian per second. The initial is 3.5 radian per second. Alpha has been determined, minus 0.024. And this change from here to here occurs at time t, and that's what you want to determine. And you can solve for t. And when you do that, you get 41.7 seconds. And that is the answer for part B. And that solves the problem. Thank you for watching.